In this video, I am going to tell you about the Pauli matrices and what they have to do with quantum spin. And they have to do a lot with quantum spin. Extremely, extremely important. And if you don't know what matrices are, don't worry, because I'm going to explain what they are. But if you do know what they are, also don't worry, because it's not going to be boring. I've tried to make this video interesting to both people who don't know what matrices are ahead of time and people who do know what matrices are ahead of time. The thing is that quantum mechanics, as we'll see, is really just glorified linear algebra. And matrices fit into the subject in such a natural way that explaining them really isn't a burden at all. I'm going to start off my discussion of the Pauli matrices by showing that they give us an efficient way to calculate expectation values of spin measurements. Having said that, as the video goes on, I hope you'll see that there's a lot more interesting stuff about the Pauli matrices than just that they give us an efficient way to calculate something. But for now, let's just start off by talking about the expectation values. So say you have an electron with a quantum spin state psi with components alpha and beta, and you do a spin measurement along the z-axis. We know that the probability of finding the electron in the spin up state along the z-axis is equal to the absolute value of the inner product of the spin up state along the z-axis with psi squared, which is just the absolute value of alpha squared. We also know that the probability of measuring the spin down state along the z-axis is just equal to the absolute value of the inner product of the spin down state along the z-axis with psi squared, which is just equal to beta squared. Now, let's say that if the experimenter were to measure the electron in the spin up state, they were to say that that electron had a spin of +1, and if they measured it in the spin down state, they were to say that the electron had a spin of -1. The question is, what is the expected value of spin for this state? And the answer is pretty straightforward. It's just +1 times the probability of a spin up measurement -1 times the probability of a spin down measurement. And we can see pretty easily here that that's just equal to the absolute value of alpha squared minus the absolute value of beta squared. And we can see that it was pretty easy to figure out the expected value of spin for a measurement along the z-axis. And the reason for that is basically because we've written the state in such a way that we can immediately see what its components are in the basis of spin up states and spin down states along the z-axis, right? We know we can write psi as follows. And this means that if we were to take, for example, the inner product of psi with the spin up state, this would just be equal to, that would just be equal to alpha times the inner product of the spin up state with the spin up state plus beta times the inner product of the spin up state with the spin down state. But we know that the inner product of the spin up state with the spin down state is 0, while the inner product of the spin up state with the spin up state is 1. So this is just equal to alpha. But there's nothing fundamentally special about the basis of spin states along the z direction. If, for example, we had a state psi that was equal to alpha sub x times the spin up state in the x direction plus beta sub x times the spin down state in the x direction, then it would be very easy to see what the expectation value of spin for measurements in the x-axis would be. So the expectation value of spin along the x-axis would just be alpha sub x, or the absolute value of alpha sub x squared minus the absolute value of beta sub x squared. And to that end, let's actually see how we could write the spin upstate along the z direction as a sum of the upstate in the x direction and the downstate in the x direction. So the spin upstate along the z direction is equal to 1 over root 2 times the vector with components 1 over root 2 and 1 over root 2 plus 1 over root 2 times the vector with components 1 over root 2 and minus 1 over root 2, right? Because this whole thing is just the vector with components 1 and 0, and that's just the upstate in the z direction. Anyway, it's no secret that this is just 1 over root 2 times the spin upstate in the x direction plus 1 over root 2 times the spin downstate in the x direction. Let's actually do the same thing for the downstate in the z direction. So that's just equal to 1 over root 2 times the vector with components 1 over root 2 and, oops, sorry, jumped the gun a bit, and 1 over root 2 minus 1 over root 2 times the vector with components 1 over root 2 and minus 1 over root 2, right? Because this whole thing is just 0, is just a vector with components 0 and 1. And this is just equal to 1 over root 2 times the spin upstate in the x direction minus 1 over root 2 times the spin downstate in the x direction. Likewise, actually, let's do the same thing for the y direction, just to be fair to the good old y direction. So the spin upstate in the z direction is equal to, let's make sure I get this right. Yeah, okay. 1 over root 2 times the vector with components 1 over root 2 and I over root 2 plus 1 over root 2 times the vector with components 1 over root 2 and minus I over root 2, which is just 1 over root 2 times the spin upstate in the y direction minus 1 over root, plus 1 over root 2 times the spin downstate in the y direction. And then, last but not least, the spin downstate in the z direction is equal to negative I over root 2. You gotta be clever now because we got all these i's around. Times the vector with components 1 over root 2. It's getting a bit cramped. And I over root 2 plus I over root 2 times the vector with components 1 over root 2 and negative I over root 2. And let's just see, okay, the top component is just going to be, okay, the top component is just 0, and the bottom component is a half plus a half, right? Okay, good. So this checks out. And this is equal to minus I over root 2 times the spin upstate in the y component plus I over root 2 times the spin downstate in the y component. Anyway, let's get back to the expectation value. So if you have a state psi, which is alpha times the spin upstate in the z direction plus beta times the spin downstate in the z direction, then as we just saw, we can write, it's a funny two, we can write this as follows. 1 over root 2 times the spin upstate in the x direction plus 1 over root 2 times the spin downstate in the x direction. That's just another way of writing this right here. Plus beta times 1 over root 2 times the spin upstate in the x direction minus 1 over root 2 times the spin downstate in the x direction. And then we can collect like terms and find this is equal to 1 over root 2 times alpha plus beta times the spin upstate in the x direction plus 1 over root 2 times alpha minus beta times the spin downstate in the x direction. So we can now see that, if we write our state initially in the z basis, and we can see what alpha and beta are, we've now found what alpha sub x and beta sub x are. So therefore, the expectation value of spin in x-axis, or along x-axis, is equal to the absolute value of, or actually, let me write it this way, is equal to 1/2 times the absolute value of alpha plus beta squared minus 1/2 times the absolute value of alpha minus beta squared, right? So that was the result I was trying to show. All right, so let's take a bit of a breather. We just saw how to calculate the expectation value for a spin measurement along the x-axis. But there's a better way. Now, I'm not going to say what this operator sigma sub x is, but let's say that we had an operator, sigma sub x, that was a function from C2 to C2. Now, by this notation, I just mean that sigma sub x is a function that takes in an element of C2, so it takes in a spin vector, and it outputs a spin vector. So let's say that we had this function, sigma sub x, that satisfied two properties. The first one being that it's what we call linear. So sigma sub x acting on psi 1 plus psi 2 is just equal to sigma sub x acting on psi 1 plus sigma sub x acting on psi 2. And the second property, which is more special, is that when sigma sub x acts on the spin up state along the x-axis, the result is just plus 1 times the spin up state along the x-axis. And I could have just written this as, the spin up state along the x-axis, but I just want to draw attention to that plus 1 out front, even though it doesn't really make too much of a difference. So, okay. So that's how it acts on the spin up vector. And on the spin down vector, it's equal to minus 1 times the spin down vector. Right? So I haven't told you what sigma sub x is. I'm just saying, let's say there were such an operator that had these two properties. Now, say we had a state psi written in the x basis with components alpha sub x and beta sub x. Oh, just while I'm writing this, let me mention that the dual vector of psi is equal to alpha sub x bar times the dual vector of the upstate in the x direction plus beta sub x bar times the dual vector of the downstate in the x direction. And the reason that these two are complex conjugated is because you have to complex conjugate all the components when you take the dual of a vector. But okay, we'll come back to that in a second. Anyway, sigma sub x acting on psi, which we can write psi in terms of its components, can be easily calculated because sigma sub x is linear. So you can just act it on both of these vectors individually and then add them together. Now, when sigma sub x acts on the upstate, it just leaves it the same, but when it acts on the downstate, it negates it. So we can immediately see, I shouldn't even write that this is equal to alpha sub x times the upstate in the x direction minus beta sub x times the downstate in the x direction. All right, so because of the nice properties that sigma sub x has, we can immediately write how it acts on the state because we've written it in a friendly basis. Now, if we compute the inner product of psi with sigma sub x acting on psi, well, this is just equal to alpha sub x bar. All right, I'm just writing out the dual state, and I'm just writing out sigma sub x acting on psi. And this is all pretty easy to compute. There are 4 terms, but we have all sorts of nice relations, like the inner product of the spin up state with itself is 1, and the inner product of the spin down state with the spin up state is 0, and stuff like that. So you can immediately see that this is actually just equal to alpha bar sub x times alpha. Right. Alpha sub x bar times alpha sub x minus beta sub x bar times beta sub x, which is just equal to the absolute value of alpha sub x squared minus the absolute value of beta sub x squared, which is equal to the expectation value of spin measured in, or measured along, the x-axis. All right, so now you can see why I've been talking about this operator sigma sub x so much when I haven't even said what it is yet. The thing is that if you calculate the inner product of psi with sigma sub x acting on psi, you immediately get the expectation value of the spin measurement in the x direction. But the thing is that you don't actually have to know, you don't need to know what alpha sub x and beta sub x actually are. Once we know what sigma sub x is, we'll automatically know that this quantity is the expectation value without having to go through, all the rigmarole of finding alpha sub x and beta sub x. All right, so you're excited? Are you ready for me to tell you what sigma sub x is? All right, I'm going to tell you what sigma sub x is. So it turns out that sigma x is actually very simple. It's just the function that takes the vector with components alpha and beta to the vector with components beta and alpha. It swaps the 2 components. So let's check that it has the properties we want. The first one is that it's linear. So if we act sigma x on the sum of 2 vectors, so here's the sum of 2 vectors, one with components alpha 1 beta 1, one with components alpha 2 beta 2. We can add the 2 vectors together into one vector with components alpha 1 plus alpha 2 and beta 1 plus beta 2, and then swapping the upper component with the lower component, as sigma sub x does, we find that it's equal to the vector with components beta 1 plus beta 2 and alpha 1 plus alpha 2. And then, and this is just equal to the sum of the vectors with component beta 1 alpha 1 and beta 2 alpha 2. And finally, this is just equal to sigma sub x acting on alpha 1 beta 1 plus sigma sub x acting on alpha 2 beta 2. So yes, it is linear, just as we wanted. Now the more special property is that if we act it on the spin up state in the x direction, it should leave it unchanged, right? And if we act it on the spin down state in the x direction, it should negate it. So first, let's see what happens here. So the spin up state is components 1 over root 2 and 1 over root 2, but the top component equals the bottom component. So when we swap them, it stays the same. So this is indeed just equal to plus 1 times the spin up state, which is just what we wanted. And likewise, when we act on the spin down state, which has components 1 over root 2 and negative 1 over root 2, when we swap them, we just find that it's equal to negative itself, right? Because when we swap them, it's the same as negating them. And this is just equal to negative 1 times the spin down state, which is exactly what we wanted. So this sigma x here is exactly what we wanted. All right, so we've been beating around the bush, but now it's finally time to talk about matrices. So, and don't be scared, by the way. So sigma sub x can be written as a matrix. I haven't told you what a matrix is yet, by the way, but you're about to see one for yourself. So sigma sub x can be written as the following matrix. Now, once I tell you what this expression means, you will immediately see that sigma sub x acting on alpha and beta equals beta alpha. This is just a new notation. That's just a new way of writing this exact same thing. So let me talk for a moment about matrices in general. So right here, I have a general 2 by 2 matrix because there are 2 rows and 2 columns. Now, you should really think about a matrix as a function which takes one vector to another. So here we have a column vector, and here we have our matrix. And this matrix is going to take this column vector to a new column vector. And the new column vector it's going to take it to is just the one with components a times alpha plus b times beta and c times alpha plus d times beta, right? This is the rule. So we can see that the matrix with components 0, 1, 1, 0 acting on alpha beta is equal to, okay, so we have a times alpha, right? But a is 0, so that doesn't matter. But then we have b times beta, and b is 1. Okay, looking good so far. Okay, then down here, right, we have c times alpha. But c is 1, or not but anyway, you can see c is 1. But d, right, d times beta, d is 0. 0 times beta. So this is equal just to the vector with components beta alpha, just as we wanted. So in principle, I've told you really all you need to know about matrices, but or all I've told you, how matrices act on vectors. But I want to give you a little tip, I guess, or not tip, but I want to just give you a little bit of advice. Okay, I'm going to tell you how I multiply matrices in my head, okay? And hopefully that will be useful to some people. You should come up with your own way to do this quickly, but here's how I do it. So I sort of picture this column vector as kind of the bottom of a stamp. And I kind of pick the stamp up. This is just what's going on in my head when I'm multiplying matrices. So I kind of pick up this stamp. Actually, let me literally draw this as the bottom of a stamp with a handle, right? So here's the handle of the stamp. And I sort of picture taking this stamp and stamping it on these 2 rows. First I stamp it on the first row, then I stamp it on the second row. So when I stamp it on the first row, there's just an alpha next to the A and a beta next to the B. So the first top component, whoops, I already screwed up, is A times alpha plus B times beta. And then when I stamp it on the second one, then there's an alpha next to the C and a beta next to the D. So C times alpha plus D times beta. All right, and that's just how I multiply these things in my head. So maybe that will be useful to some people. Now, remember earlier when I showed that the expectation value of spin in the x-axis was equal to 1/2 times the absolute value of alpha plus beta squared minus 1/2 times the absolute value of alpha minus beta squared. Let's see what expression for the expectation value we get using sigma sub x. So if we have that psi has components of alpha and beta, then the inner product of psi with sigma sub x acting on psi is just equal to the row vector with components alpha bar and beta bar, and then the matrix, with components 0, 1, 1, 0, and then the column vector with components alpha and beta, and then this is just equal to this. And the dot product, or the inner product of these two vectors, is alpha bar times beta plus beta bar times alpha. And this is a different expression than this, right? Certainly this one seems a lot simpler, but I just felt like showing you that, closing the circle a bit and showing you that these two things are exactly the same. So the question is, does this equal alpha bar times beta plus beta bar times alpha? So if we rewrite the expression, I'm just rewriting, this top expression right now. This has 4 terms when you expand it out fully, and this has 4 terms when you expand it out fully. So these 4 terms are alpha bar alpha plus alpha bar beta plus beta bar alpha plus beta bar beta. And these 4 terms are alpha bar alpha minus alpha bar beta minus beta bar alpha plus beta bar beta. And notice that there's a minus sign right here. Oops. So this term cancels with this term cancels with this term, and all of here we have a half of this term and minus a half of this term. So yeah, we can actually see that these two things are the same. But notably, actually, as promised, I think you can agree that this expression is a lot easier. So we spent a lot of time talking about measurements in the x direction, but we have 2 other perfectly good axes to talk about, right? We have the y direction and the z direction. So what are the matrices that will give us the expectation values in those directions? Well, for the y direction, sigma, the matrix we'll call sigma sub y, has components 0, negative I, and 0. Seems pretty cool. And the matrix in the z direction, definitely the simplest out of all of them, has components 1, 0, 0, and negative 1. So just as we have previously showed that sigma sub x acting on the spin up direction, the x direction, is plus 1 times this very same vector, and acting on the spin down direction, spin down vector in the x direction is minus 1 times the very same vector. We should show the same analogous thing for these other 2 matrices. So that's what I just want to show right now. So we're just checking that these 2 matrices really do work as they should. So to start off, sigma sub y acting on the spin up vector in the y direction. That's equal to matrix with component 0, negative I, and 0, acting on the vector with components 1 over root 2 and I over root 2. Okay, actually, I'm only going to do this this first time. But picture picking up this stamp, right? And we're picking up the stamp. The components are 1 over root 2 and I over root 2. And we're going to stamp it on this top one, right? And that gives us 0 times 1 over root 2 minus I times I over root 2. And now we're going to stamp it on the second one. And that gives us, that gives us I times 1 over root 2 plus 0 times I over root 2. And this is equal to, okay, negative I times I is 1. So 1 over root 2. And the bottom here, we just have I over root 2. And yeah, that is just equal to the spin up vector in the y component, right? This vector is just the same as this vector. Okay, so from here on out, you're going to have to do all the stamping in your head. But okay, let's see what happens when we act with sigma sub y on the spin down vector in the y direction. So that's just 0, negative I, and 0. And here we have 1 over root 2 and negative I over root 2. The negative I makes all the difference. So, are you stamping? All right, so stamp in your head with me, right? We got 0 times 1 over root 2 minus I times negative I over root 2. And then we have I times 1 over root 2 plus 0 times negative I over root 2. And that's equal to negative 1 over root 2 on the top and I over root 2 in the bottom. And up, that's just equal to negative 1 times 1 over root 2 and negative I over root 2. And yeah, that's equal to negative 1 times the spin down state in the y direction. So yay, okay. This matrix checks out. Now, let's see what's up with the z direction. So, okay, one thing. So you can see that the diagonal components, right, the going from the top left to the bottom right, are the only non-zero, are the only non-zero components. Actually, I should say entries. So, yeah. So I guess I should just say that the 4 numbers in a matrix are called entries. I shouldn't have called them components. But anyway, when you have only zeros not on the diagonal, it's really easy to multiply matrices. So sigma sub z acting on 1 and 0. Oh, I might as well just, okay. Sigma sub z acting on the spin up vector. This is just 1, 0, 0, negative 1 acting on 1, 0. You can just multiply this number by this number and this number by this number. That's just a simple thing about using completely diagonal matrices. So 1 times 1 is, sorry, why did I write 0 there? My bad. So 1 times 1 on the top and negative 1 times 0 on the bottom. You don't even have to, this is just a quick thing to keep in mind when you only have zeros on the off-diagonal terms. Anyway, this is just 1, 0, which is just plus 1 times the spin-up state along the z direction. Okay, which is just what we wanted. Now, what about the spin-down state along the z direction? Well, it should be pretty easy to see that when we act with sigma sub z on the spin-down state, we have 1 times 0 and negative 1 times 1, which is just equal to 0 and negative 1, which is just equal to negative 0 and 1, which is equal to -1 times the spin down state along the z direction. So, okay, all three of these matrices work as intended, and these are called, let me choose a special color. These are called the three Pauli matrices. Now, just to belabor the point, the expectation value of spin along the x-axis is the inner product of psi with sigma sub x acting on psi. Along the y-axis, you just got to put sigma sub y in there, sigma sub y, and along the z-axis, you just got to put sigma sub z in there. Anyway, I've spent a lot of time in my life with these Pauli matrices. And I gotta say, there's something about the algebra of these Pauli matrices that's just really charming to me. Even the name Pauli matrices is just a very pleasing name to me. When I think of these Pauli matrices, the one word that really comes to mind is cute. I think these things are just like, I don't know, I think they're very cute, right? You know, there's all these ones and zeros, and the second one is this I. And, you know, they kind of look like, you know, they look like little figures, right? You know, maybe like they have like, you know, a little face. I don't know if anyone else feels this way, but I've always felt that I just think these things are a lot of fun somehow. They're very pleasing to me. Oh, anyway, that's enough fun. Time to get back to business. All right. So it's time for me to tell you some extremely important terminology. And I guess half of you will already know this. But when you have an equation like sigma sub y acting on the spin down state in the y direction equals -1 times the spin down state in the y direction, when you have an equation like this, you have a matrix acting on a vector and it equals a constant times the same vector, you would call this vector, you'd call it an eigenvector, right? So you would say that this vector is an eigenvector of sigma sub y. You would also call this value, right? Here it's -1. You would call that an eigenvalue. Now apparently, I looked it up, and apparently eigen is, I think, a German word which means same. So that actually makes a lot of sense. So you would this is called, in other words, a same vector, so to speak, because when the matrix acts on this vector, the vector stays the same. It's just multiplied by a value. And I guess that would be the same value, like the value with which it's the same. Yeah. That's extremely important terminology if you didn't know that. All right, now I want to talk about matrix multiplication in general. And even if you know about matrix multiplication, I have a point to talking about this, so I might advise still to not stop watching. But okay, say that A is an m by n matrix. So as per convention, m is the number of rows and n is the number of columns. That means, as per standard notation, if you have aij, where I is an integer that goes from 1 to m, and j is an integer that goes from 1 to n, you would say that aij is the ijth entry of matrix A. So for example, if m equals 3 and n equals 2, then A would look something like this. It would be a 3 by 2 matrix, and its components would be A11, A21, A31, A12, A22, and A32. Now, matrices can be multiplied together, but only if they have the right dimensions. So let's say A is an m by n matrix and B is an n by L matrix. Because the number of columns of A is equal to the number of rows of B, you can multiply these two matrices together, and you would write that as AB. So the way you should think about this, or one way you can think about this, is that when you have an m by n matrix and you multiply it by an n by L matrix, you kind of contract the two ends, right? So you contract the number of columns of A with the number of rows of B. And the overall result is an m by L matrix. So AB is an m by L matrix. And the rule for calculating AB is as follows. The ijth component of AB is equal to the sum from k equals 1 to n of A ik times B kj. All right, so you can see that k, right, which is in the summation a kind of dummy index, right, because it's within the summation. You have to add n things together to calculate the ijth component of AB, right? So I keep calling them components, really I should call them entries. Every entry of AB, you have to sum n things together. And that's sort of how like this n right here, disappears. So you can see that, because I had to be an integer from 1 to m, and this j had to be an integer from 1 to L, you can see that this overall AB really is an m by L matrix, just as we said it would be. All right, so if you didn't already know what matrix multiplication was ahead of time, it might just seem like I was defining some random rule. But it's actually basically what we were just doing earlier. So here's the thing. A column vector can be thought of as an m by 1 matrix. So remember that the first number is the number of rows and the second number is the number of columns. So a column vector is just one column. Likewise, a row vector is a 1 by m matrix because the first number is the number of rows and a row vector is just one row. So if you have a square matrix, an m by m matrix, and you multiply it by a column vector, which is m by 1, then when you contract the two middle indices, the overall result is an m by 1 matrix, which is just a column vector. So we can see that when we multiply a square matrix by a column vector, the result is another column vector. And this might help you. And just to connect things up, this whole contracting the middle indices thing, right, where this m, we have to have the number of the number of columns of our matrix equal the number of rows of our column vector. That's what we need in order to get our stamping procedure to work. So say we had a 3 by 3 matrix, right? And we were to multiply it by a column vector with 3 rows. When we lift up this column vector, right, like this, we need, in order for our stamping procedure to work, we need each of the 3 rows of our column vector to match a column of our matrix. And that's just what we need in order for our stamping procedure to work, right? So, in other words, you should think of this contraction right here as just the same old stamping we were doing earlier. Now, there's something else you can do once you think about vectors as matrices. Say that you had a row vector, which is a 1 by m matrix, and you were to multiply it by a column vector, which is an m by 1 matrix. Contracting the two m's, you can see that the overall result is a 1 by 1 matrix, which is also just known as a single number. And that makes perfect sense with what we've been doing this whole time. So if you had a row vector, for example, which had 3 components, and a column vector with 3 components, then this whole thing right here is just a number. And the quote-unquote stamping procedure, where you were to, I guess, bring up this column vector right here and then stamp it, that's just the inner product that we've been doing this whole time. Now, there's something else interesting that you can do with a row vector and a column vector that a lot of people don't mention, which is that if you do this the other way, if you take a column vector, which is an m by 1 matrix, and you multiply it by a row vector, which is a 1 by m matrix. See, here you had the row vector on the left and the column vector on the right. And here you have the column vector on the left and the row vector on the right. Totally different. Because here, the 1 contracts with the 1, and the overall result is an m by m square matrix. So let's actually see how that would work. So say that you had a column vector with components a and b, and you had a row vector with components c and d. Now this whole thing we're going to see is a 2 by 2 matrix. Now, what is the 2 by 2 matrix? Well, because we're, let me just write it again. Because we're only contracting one index, we don't actually have to add anything up to calculate any particular entry of our resulting 2 by 2 matrix. There's going to be no addition. So how it's going to work is basically we're just going to take this vector, right? And we're going to sort of put it here twice. And then we're going to take this vector and we're going to put it here twice. And we're just going to multiply the entries of this vector with the entries of this vector when they overlap. So the answer is going to be a times c. Actually, let me just put it this way. Let me put this one in first, right? So I'm going to start filling in a, b, a, b. But I'm not done yet because now I got to multiply it by c and d and c and d. So, okay. So this is how you take a row vector and the column vector and multiply them in the other order. And the result is a square matrix. So it's very interesting to see that from the general matrix multiplication rule, there are so many different operations that are special cases of that one general rule. Now, the really important thing about matrix multiplication is that it's associative. So, associative. This is just a vocabulary word, which means that if you have 3 matrices, A, B, and C, that can be multiplied together, because assuming A, B, and C have the right dimensions to be multiplied together. You have AB times C is the same thing as A times BC. In other words, the order in which you multiply matrices doesn't matter. You can multiply A and B first and multiply it by C, or multiply B and C first, then multiply that by A. And the end result will be exactly the same. So let's say A has dimension P times Q, A is PQ, B is Q times R, C is R times S, and because here we have Q and Q here, and R here, these can be multiplied in the way we want them to be. And the total matrix A, B, C, the ijth component of that is equal to the sum from L equals 1 to Q, right? So first I'm doing this sum. So from L equals 1 to Q of, another sum. Right, now we're doing the R sum. From K equals 1 to R. A, I, L, B, L, K, C, K, J. So, right, so this is ABC, and if you notice, you can actually, if you switch the order of summation, which you can always do, you could write this, for example, as the following. Right, so the thing is that I wrote this all in parentheses because, as you can see, we're summing over the dummy index L, and L is only inside the parentheses. So that's why I'm allowed to draw those parentheses. Anyway, this whole thing is just the ikth component of AB. So you can see that this, as we've written it here, we first do the multiplication of A and B, and then we multiply it by C. So that's one way we could do it. But we could also, but we could also do the summation in a different way. We could have the sum over L first, and then have AIL out here, and then in parentheses do the sum from K equals 1 to R of BLK CKJ. So see, now I'm summing over the dummy index K, and K only appears inside the parentheses. So actually, why did I erase that? So while this was the ikth component of A and B, this is the ljth component of B and C, or BC. So just from rearranging the summations, right? Just from rearranging the summations, we have proved associativity. An interesting thing is that just as we've rearranged the order of summation, if you were to compute this product like this and then compute it like this, you would actually be doing summations in a different order, as if you actually had real matrices A, B, and C in front of you. To compute it in these two different ways would actually be to sum stuff in a different order, just as we've written the sums in a different order here. All right, so by now you're really confused. You're saying, I just want to learn about quantum mechanics and how you're like doing all this horrible stuff with matrices. But now I'm going to tell you the point that I've really been wanting to say this whole time. So say that you have a column vector, which is an m by 1 matrix, right? That's a column vector. And then you have a row vector, which is a 1 by m matrix. It's a row vector. And then you have another column vector, which is an m by 1 matrix. Once again. So there are two ways that you could evaluate this product of matrices. The first way is by contracting these two m's, and the whole result is a 1 by 1 matrix, which is just a number. And then contracting this one with this one, that's really just multiplying a constant by a matrix. This whole thing is an m by 1 matrix, which is just a column vector. Right, so that's the first way you could do it. But the other way you could do it is by contracting this 1 right here, and this whole thing is an m by m square matrix. And now, contracting this m with this m, multiplying this square matrix by a column vector, the end result is an m by 1 matrix, aka a column vector. And by associativity, we know that these two things are exactly the same. All right, now having said all of that, I now want to compute the following thing. Oh, it's coming back to quantum mechanics, as you can see. I want to compute the following thing. Now you see, this is a row vector and this is a column vector. Likewise, this is a row vector and this is a column vector. So this whole result is going to be a 2 by 2 matrix. So this is just equal to column vector with entries 1 over root 2, 1 over root 2, and then 1 over root 2, and 1 over root 2. And then here we have 1 over root 2 minus 1 over root 2 and 1 over root 2 minus 1 over root 2. And then we're gonna multiply these in the way I said earlier, where first, you take this and you put it here and here, and then you take this and you put it here and here. So let's do just that. 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2. That was me putting that in the 2 spots. And now I'm going to put this in the 2 spots. So times 1 over root 2, 1 over root 2. Oh, I didn't even write a 2 there. Got kind of bored. Okay, 1 over root 2, 1 over root 2. And now we're going to do this one. So minus, so we got 1 over root 2 minus 1 over root 2, 1 over root 2 minus 1 over root 2. And then here we got 1 over root 2 minus 1 over root 2. 1 over root 2 minus 1 over root 2. So, all right, I guess this got a little messy, but these are where the dividing spaces are. Anyway, this is just equal to 1 half, 1 half, 1 half, 1 half minus 1 half minus a half minus a half and 1 half. And this is just equal to 0, 1, 1, 0. And that is just equal to sigma x. Ooh. Now, it seems pretty mystical, right? That this thing equals sigma x. But actually, if you think about it a little harder, it makes perfect sense. Because if you were to take, if you were to just take this thing, right? And you were to put, for instance, the spin down state in the x direction right here, right? This would equal the following thing. Right? And then this right here is 1, but this right here is 0. So this whole thing then equals just negative the spin down state in the x direction, right? And likewise, if you were to put in the spin up state in the x direction, then you would have just got, the same state out. Because see, there's a negative here, but there's no negative here. Any case, so this result is just, exactly the same as this equation that we already had. So, in other words, the associativity of matrix multiplication is what allows us to manipulate this notation in such a nice way. And as I'm sure you could guess, this relationship is also true for the y direction and for the z direction. So now let's show it for the other directions. So the only wrinkle is that in the y direction you gotta complex conjugate the dual vectors, but that's a fact that we're already very well acquainted with by this point. So here we have 1 over root 2, I over root 2, 1 over root 2, negative I over root 2, minus 1 over root 2, negative I over root 2, 1 over root 2, I over root 2, and then we have 1 over root 2, I over root 2, 1 over root 2, I over root 2, and then 1 over root 2, negative I over root 2, 1 over root 2, negative I over root 2, minus 1 over root 2, negative I over root 2, 1 over root 2, negative I over root 2, 1 over root 2, I over root 2, 1 over root 2, I over root 2. And this is equal to a half minus I over 2, I over 2, and then 1 over 2 minus a half I over 2, negative I over 2, and then 1 over 2. And that is just equal to 1, it's just equal to 0, negative I, 0. Oh my god, it's sigma sub y equals sigma sub y, which is exactly what we wanted. Now, y is always the hardest one, but now we're going to do z. And z is anything involving z is always really easy. It's the treat at the end. So now we're going to compute the following matrix. Okay, so that's equal to 1, 0, 0, 1, minus 0, 1, 0, 1. That's equal to, oh man, I actually screwed it up. Wow. I shouldn't have been so dismissive. Okay, the main obstacle is your own ambivalence. Okay, so here we have 1 times 1, 1 times 0, 0 times 1, 0 times 0, minus 0 times 0, 0 times 1, 1 times 0 and 1 times 1. So that's just 1, 0, 0, 0 minus 0, 0, 0, 1 equals 1, 0, 0, negative 1. And what do you know? Sigma sub z. Ta-da! Actually, let me just sneak in another funny little point, which is that if you were to make each of these minuses a plus, so we had plus here, and plus here, they would all be equal to the same matrix, which was 1, 0, 0, 1. And I claim that this is true due to the conservation of probability, that along any axis, the probability of measuring something up plus the probability of measuring something down always has to be 1. So I claim that, and I'll let you ponder this for yourself. You could actually check this for yourself, that adding them instead of subtracting them all give this matrix. That's just sort of an interesting thing that I kind of want to wedge in here. But anyway, I'm going to move on. So one final piece of terminology. Sometimes I feel like I'm like a vocabulary teacher. But okay, so you remember how this is called an inner product? And it's kind of a stupid name, right? Inner product. Well, it's about to get a lot less stupid. Because this thing right here, what do you think this is called? All right, guess. It's called an outer product, which actually I find kind of nice, you know, because these are facing inwards and these are facing outwards. And as a notation, you know, I approve of this. I think that's pretty smart. So, okay, inner product, outer product. That's all I wanted to say. Well, I've said everything I wanted to say about Pauli matrices. Hope you can agree they're lots of fun. Even though we spent such a long video talking about them, strangely we haven't even scratched the surface of their importance in general. I'll just say a few words about it so you can look this up if you want. But they're really important for the Lie algebra, whatever that is, of SU2, whatever that is. And they're really important for representation theory and what it really means to be a spin 1/2 particle in the first place, but I'm not going to talk about that right now. Although all of our talk about eigenvectors and eigenvalues, you know, that will not have been for naught. Right. Let me just pose a leading question, right? Say you have a unit vector in 3D space with components nx, ny, and nz. Now, what is the spin state that could be said to be rightfully pointing in this direction in space, right? So far, I've only talked about spin states pointing along the x-axis, y-axis, and z-axis. But what about pointing in any arbitrary direction? The answer is that it's the state which is the eigenvector, which is the eigenvector of this matrix, right, with eigenvalue 1. So the eigenvector with eigenvalue 1 of this matrix right here is the state which you could say is pointing in this direction in real space. So my next video on the block sphere is going to be about all of that. But I know this has been a long and intense video, so if you've made it this far, give yourself a real pat on the back. And before you rush to watch the next one, make sure you do something restorative to, get your brain back in order. All right. Thank you for watching.